me show you how to be a good breezy and change your predictions.
Hello, my dear Bayesians. Today, I wanted to make a small erratum because, yeah, apparently I am human and I sometimes make mistakes. Who knew? How disappointing, I know. But well, last week in the main episode 141, I said in the intro that Sam is the driving force behind ChiRho, which is kind of unfair to the other ChiRho contributors. And as Sam mentions himself in the interview, ChiRho is a team effort before anything, and Sam is one of the core contributors in this great team. So now, I hope the record is straight. I thank you for your understanding, and now let's hear back from Sam with this week's BITESIZE episode. I hope you enjoy.
So one point of clarification there, because it's a little subtle, is that ChiRho doesn't actually use the do calculus.
Interesting. I thought you guys were. So yeah, how do you do that?
Yeah, I can explain. So
yeah.
So the do calculus is a set of symbolic rules developed by Pearl and students several years ago that translate causal questions into probabilistic questions for what are called non-parametric structural causal models. So the idea is that if all I have is a graph, which denotes the structure of causal relationships between my variables, then the do calculus gives me a sound and complete algorithm for translating that into probabilistic expressions that I can estimate from data. One of the limitations of the do calculus, it's a great tool, and I think the symbolic approaches are awesome. I see what we do in ChiRho as supplementary. One of the limitations of the do calculus is there's a key word I said in the definition, which is non-parametric. And a lot of the times, the models we write about the world include parametric assumptions that actually make it really much easier to do causal inference generally. So an example of this is if you're familiar with regression discontinuity designs, this is what's called a quasi-experimental design, where you have observational data where you have a continuous covariate. So for example, a classic example is the test scores a student get on an exam. And you have a treatment, which is, in this example, whether they are admitted into the next grade or not, or whether they're held back. And then an outcome, which is their education outcomes in the long term. So a regression discontinuity design takes advantage of the fact that we know that there's a fixed threshold in this test score, where if you're to the left of this threshold, you get held back a grade. And if you are to the right of this threshold, you advance to the next grade. And a key conclusion of this is that you can look at individuals who are very, very close to that threshold on the left and the right, and kind of intuit that because they have such similar values of test scores, which may confound the relationship between whether they get held back and whether they how their education outcomes are, you can assume that they're basically the same because they're infinitesimally close to each other, but they have this kind of differentiated treatment. So it turns out that if you're willing to make these parametric assumptions about smoothness of the functions, or even just this discontinuity existing at all, you can estimate what's called the conditional average treatment effect arbitrarily close to that discontinuity. That kind of assumption is really easy to write as a program. You can't, as far as I know, write it directly as a graphical model. Like the structure of the variables influencing each other doesn't tell you enough to encode that. Okay, so we use a different way of thinking about causal inference, which I call, in my thesis, Bayesian structural causal inference. So the idea, actually, is it okay if I share some figures?
Yeah, for sure. That's gonna be sweet. Yeah, and actually, that's where So people listening, you might want to switch to the YouTube channel, and you'll have the chapters in the description, so you can jump right into that moment in the episode.
Okay, so this is a kind of a cartoonish view of what a structural causal model does in what we call the factual world. So you can think of this space on the left as the sort of space of all the causal models in the world that you're considering, and the space on the right is the data that you would observe. So here you can see it's, again, kind of cartoonish, but you can imagine a single structural causal model inducing a distribution over data. So being good Bayesians, we can put probability distributions on these things, and again, quite cartoonish. But now, if you imagine a distribution over structural causal models, that induces a much broader distribution over the data you would see.
Yeah, that makes sense. Yeah.
Great. So then, again, kind of, hopefully this is all very intuitive. If you start with a distribution over structural causal models and then you observe factual data, you can propagate, you can condition on that data and propagate that into a posterior distribution over these structural causal models. And so far, this is nothing but ordinary Bayesian inference. There's really nothing new here. But interesting things happen when you start to add these intervention transformations. So you can think of an intervention as a kind of function between models. It takes a structural causal model and turns it into a different structural causal model, which, as you can see here, is kind of in a different point in structural causal model space. So the original structural causal model induces a distribution over data, and the intervened structural causal model induces a different distribution over data.
Right.
And you can construct what we call a causal query, which is some function of your distribution over data and counterfactual data. So this might be like the average difference between outcomes under intervention and under your original world. So again, the story is similar. If we induce a distribution over structural causal models, that propagates to a distribution over intervened structural causal models, which then propagate to distributions over factual data and counterfactual data, and then a distribution over the causal query. And it turns out that if you've set up these interventions in a certain way, I mean, essentially you just need to preserve measurability, then the whole thing can just be treated as one big probabilistic inference problem. So now, rather than having just a joint distribution over models and data, you have a joint distribution over models, data, intervened models, counterfactual data, and counterfactual queries. But that's just a joint distribution. And the machinery of probabilistic modeling and inference tells us how we can manipulate these joint distributions and get posterior distributions over all the things we care about. So your factual data propagates to the posterior over structural causal models, which then gives you a push-forward distribution onto intervened structural causal models, which then pushes forward into a distribution over counterfactual data. And then you get a sort of posterior distribution over answers to your causal query.
Yeah, this is great.
Yeah, so this is
Thanks for sharing
this idea of just like taking causal models and turning them into probabilistic models is not unique to ChiRho or this or my thesis, but I think in ChiRho we really codified this and made it very explicit. So one way of thinking about what ChiRho is doing is it's automating this edge here, intervening from a structural causal model to a different structural causal model, and it's automating constructing all these different parallel worlds that construct this big joint distribution over different worlds. But then once you have that, like I said, it's just probability once you get to this space. And then you can use all of Pyro's existing inference tools to approximate inference however you'd like.
Yeah, this is amazing. Thanks a lot for sharing that.
Yeah, no problem.
Makes me want to try this right now. I need a use case. Yeah,
Spin up
I'm
a
actually-
REPL. Let's go.
yeah. Man, yeah. Like, I'm gonna use that very soon. I have some ideas of projects I can apply that to. And that sounds, yeah, I think it's super interesting, and I do think, it's filling the need we have right now with the generative AI, well, and making sure we can harness its power in a more structured way. So it's not going to be helpful for every problems, but I'm guessing there's a lot of problems for which is going to be extremely helpful.
Yeah.
And that was great.
I realized.
Yeah, go ahead.
I kind of skipped your actual question. You asked me about ChiRho's design, and I talked about what ChiRho is.
Yeah, that's fine. I was gonna ask you again that,
Okay.
and then maybe we can walk through a duoperator concrete example after that. But yeah, first, if you can come back to the designing of ChiRho.
Yeah.
And yeah, I think you answered the Pyro part, why you based it on Pyro, but mainly the main philosophy, if you want, the Zen of ChiRho, let's say.
Yeah. Yeah. So it's worth saying the caveat, which is that one reason we designed it off of Pyro is because Eli Bingham, who was another core developer of ChiRho, arguably, the lead developer and architect, was also a core developer of the Pyro probabilistic programming language. So there's a certain practical element of just familiarity.
That helps. Yeah, for
It
sure.
helps, certainly. At the same time, I think there are some interesting things about Pyro's design that made it easy to build off of. So the main goal with ChiRho was to make the causal probabilistic programming language modular and extensible. So modular meaning that it could be decomposed into kind of atomic parts that can be combined at will to solve all sorts of different problems. So that means users can write models in a modular fashion and combine it with many different questions. They can take many different questions and reduce them to probabilistic inference, and then have modular choices about what probabilistic inference algorithms they use. So that combination of like freely being able to mix and match models, questions, and algorithms gives you this like combinatorial explosion of choices as a modeler. And they're choices you can kind of enumerate pretty quickly, right? Moving from an average treatment effect to a conditional average treatment effect is, again, just a few lines of code. Going from a conditional average treatment effect to mediation analysis is another few lines of code. Modeling non-compliance in your treatment assignment is another single line of code. You just add a distribution to your intervened treatment assignment. And because this is all just code, all the kind of composability you would normally get from software follows in ChiRho programs as well. You're not really constrained to just thinking of causal inference questions as a kind of catalog of different things to choose from. It really is a programming experience, which we were really intentional about. The other thing we were trying to achieve, which I think we have, is to make ChiRho extensible. So it was pretty clear when first building ChiRho that we weren't going to build in all of the capabilities that we wanted from the get-go. The literature is too large and complicated. Research continues and progresses the field. So we wanted to design it in a way that as new research was developed, it could be tightly integrated into ChiRho without kind of uprooting the whole system. So there are two ways that we've seen that happen already, which I could nerd out about for a very long time, but maybe we can delay for later. One is extending ChiRho's modeling language to support continuous time dynamical systems. And we have a paper that's currently in review and will be coming out soon, kind of describing all the math of what's going on there.
So, what do you mean by that? What's the problem right now, and what would that solve?
Yeah, so the problem is that um, by default, intervention semantics for probabilistic programs don't tell you how to deal with continuous time. And they don't tell you how to deal with models written as differential equations. Um,
So that
because,
means, does
yeah,
that mean when you have, so for instance, time series, or is it also a problem if you have continuous variables? So like, do you mean that your outcome and treatment always have to be binary, or can they be
no.
continuous? Like,
Yeah,
yeah,
so
like,
variables can be continuous in ChiRho. That's really no problem. Um,
okay,
Defining an intervention on a continuous variable is just as easy as defining an intervention on a binary variable.
right, yeah,
Um, Estimating can be harder, but that's kind of a separate question. Um, what I mean is that uh, if you have a time series model, like a differential equation, that um, describes the behavior of the system at every point in continuous time, um, a key challenge is that when you're simulating this system, you don't actually visit every point in time. You would approximate this continuous time system with a collection of finite time points. And if you did the naive thing of just applying an intervention to any of those finite time points, you might miss the time where you want to apply an intervention. Um, and sometimes you might want to have an intervention where you don't know in advance when it's going to occur. So, for example, if you're modeling a control system that turns on an HVAC controller when the temperature of some room gets above some threshold, but you kind of need to like wait until you see what the temperature of the room is before you can decide when to intervene. Um, and that kind of representation of an intervention just wasn't covered by the existing literature.
okay, okay, yeah,
Yeah.
yeah. That
So
sounds harder. That definitely
yeah,
sounds harder.
it's harder, but at the same time, one of the really cool things about ChiRho is um, if you define what it means to intervene in such a system, which is work. I mean, there's a fair amount of math to make sure that that works out correctly. But once you've done that work, you get all of the other thing ChiRho provides to you for free. So now all of a sudden you can ask mediation analysis questions of differential equations models. You can ask attribution questions. You can ask about probability of necessity or probability of sufficiency. Um, and this works because, like I said, ChiRho is modular. We have this abstract notion of an intervention. We define what that means on any given modeling system. And then we have queries that combine these abstract interventions in a way that's, so the query model agnostic, even though it's implemented concretely on any given model. Um, so that's very exciting. I happen to like those kind of models, but also I just think it's a really interesting demonstration of kind of how far we might be able to take causal reasoning into different modeling families that people don't normally think of as causal. Um,
Yeah,
so the yeah,
that sounds super. Yeah, that sounds super exciting. Honestly,
yeah,
I can't wait to see that.
yeah. I'll hold off on the other thing because I think we're going to talk about it later. But we've also
Okay.
been able to extend ChiRho to support what's called efficient estimation. Um, so now, with more or less the click of a button, ChiRho provides efficient estimators for more or less any probabilistic program and any query you write in ChiRho, which is very exciting.
Okay. Yeah, I mean we can talk about that now. That sounds interesting. So yeah, maybe define what you mean by efficient estimators, why that's useful, and in which cases, yeah, like why would people use that concretely?
Yeah, okay, so when solving causal inference problems, you inevitably have to solve uh, some estimation task, right? So if I'm interested in the effect of some treatment on some outcome, and there are confounders, I need to adjust for all of the potential confounders that I'm observing. One way of doing that is to build a regression model of the outcome given all the other things. So essentially, uh, fit some distribution P of y given this huge vector of covariates and one individual treatment. And without even going Bayesian, even just from a frequentist perspective, you can show that as the number of covariates gets very, very large, um, even though you're only trying to estimate a single treatment outcome relationship, your error rate, like the ability to get closer and closer to the truth, doesn't decay that fast. Essentially, you have what are called a lot of these nuisance parameters, a lot of parameters that are necessary to fit the model that don't really matter for the question you're trying to answer, that you'd like to kind of ignore, right? You can think of it as a kind of like statistical budgeting, right? I've got a finite amount of data. I want to allocate the statistical juice I get out of that data towards the questions I care about and not all these other nuisances that don't really matter. So an efficient estimator is an estimator that behaves as if you were only estimating a single variable in this regression, a single parameter.
Okay.
So it approaches the truth as fast as if it were just a 1D regression problem with some constants thrown in. But that's the general idea.
Okay, yeah, so it's gonna make, like, ideally this is something that users wouldn't even really need to be conscious about, right? That's something that ChiRho would do under the hood for them, so that it's much faster to have their analyses run, but like the normal user wouldn't even need to worry about that. Am I right?
Yeah, that's right. So right now it's quite computationally intensive. So we leave it as a separate module that you can either use or not use. But yeah, that's the general idea, is that systems like ChiRho should automate the hard math of finding these efficient estimators.
Yeah.
So that you can focus on modeling and asking questions, and you don't need to have a PhD and a lot of expertise in functional analysis.
Let me show you how to be a good Bayesian.